So this is our second lecture in Chapter 2 on force vectors. We did pretty much everything associated with pre-Cartesian vector representation of vectors, and now we're going to emphasize Cartesian vector form representation. So to start us off, here's a problem. It's a two-dimensional problem. We have the x-axis, the y-axis, a force represented as a vector having magnitude 210 newtons, and it's at an orientation given 55 degrees, that angle right there. Calculate or express that force vector in Cartesian vector form. That's all we need to do. So basically the Cartesian vector form would be something in the I, something in the J, and it'd have units of Newton. Well, what does this I represent? It's a unit vector. I can't spell today. Vector in the x direction, the x coordinate direction. And what is the J? A unit vector in the y coordinate direction. And so what we see is we're decomposing this force vector into the sum of two force vectors, one completely along the x and then the other completely along the y. So I think we can work this one together. What would be, normally I would call that like fx, that's the magnitude of the component in the x, and this is fy. So how would we find fx? What is fx? 210, the cosine of that angle, 55 degrees. We look for our right triangle. We construct the right triangle. So from the ending of the force vector, we drop perpendicular down. We make a right triangle. This is the opposite. This is the adjacent. This is the hypotenuse. And so fx is 210 times the cosine of 55 degrees. And then fy would be 210 times the sine of 55 degrees. Let's go ahead and press forward. Sometimes you'll see a problem where they have a force vector without an angle. What did they show describing the direction of this force vector? A little triangle. And this triangle is what we call a 3, 4, 5 triangle. There's plenty of them, but it's very common to have a nice little triangle like this. Now, what does that 3 mean, that 4 mean, and that 5 mean on this little triangle?
It's a right triangle, and all of the...
Yeah, it's like a...
triangle.
It basically gives you the orientation expressed by what we call a similar triangle. It's similar to this triangle right here, the one we used just previously. And this 3, 4, 5, you could think of it in centimeters, millimeters, meters. I like to think of it in some length, but you know, they're similar to a force vector where the triangle is made up of the forces on all three sides, Fy, Fx. I like to think of this as a similar triangle, which is how do you say it? Showing lengths. And it's really the proportion that's important, not the magnitude. So on a sheet of paper, can you please just sketch two triangles which are similar? I know I just showed you two triangles that are similar, but one often we're going to use a lot, you'll see a lot in a textbook, the section of the hypotenuse is overlapping on two similar right triangles, but they don't have to be. You can have two similar right triangles which look like this. See? Yeah. And so what is true about those similar triangles? They have the same length of the hypotenuse? No. They have the same shape with the size related by a scaling factor. It's like you multiply this or divide to get the other scale. You know, shrink it, stretch it, but it has the same shape. Yeah, so the correct answer is B. And what is the relationship between the interior angles of similar triangles? The larger triangle has larger interior angles. The smaller has larger interior angles, or they have the same interior angles? Yeah, they're the same interior angles. And what we find is you get good at using similar triangles, and it helps decompose force vectors. So, using this representation with this similar triangle, go ahead and express this force, Cartesian, vector form. So we're looking for what is the magnitude in the I plus what is the magnitude in the J. I am going to pause and I'll walk around, and when I get 5 people that have this right, we'll move on. The ratio of 3 over 5 is the same ratio as the hypotenuse, which is in the force 110 newtons, divided by the magnitude in the x, isn't it? The 3, whoops, I got it backwards. Put a 5 over 3, right? The hypotenuse is 5. The hypotenuse of the similar triangle for the force is 110 newtons, and the horizontal is 3 in the similar triangle, and then the horizontal for the force triangle is fx. So what you pick up for f of x is you pick up 3/5 of 110 newtons, which, what does that come out to be? 66 newtons. And then likewise for this side, it's like for both of those, you can either do opposite over hypotenuse or whatever. You can do the 4 over 5 is equivalent to the Fy over 110. It's the ratios are the same. So we pick up 4/5 of 110, which comes in at what, 88? This is J. And we would want to put newtons. We only need to put it on one place. We can put it in both places if you like, but put it on the outside one place. And this is my force vector, and that's what I was looking for.
I did it another way. I don't know if it worked.
Okay.
I did sine theta, inverse sine theta is equal to...
Yeah, probably what you went in and got this angle, and then you said that angle is the same. And what you'll see is it's slightly longer, but you get the same answer. Yep. Didn't you get the right answer?
Yeah.
Yeah. Yeah, because these interior angles, like these two blue angles, are the same as this angle and that angle. And then we already know that they're both right triangles, so they're both 90 degrees there. Yeah. Okay, now we are getting to something a little more complicated. It's still 2D, but here is a concurrent force system consisting of 3 forces, F1 and F2 and F3. And you're asked to calculate the resultant force, which is the sum of those 3 forces. So somebody says F of R is equal to F of 1 plus F of 2 plus F of 3. Now, if you were doing it with triangles and the geometry, you would first add 2 of the vectors, get a resultant vector, take that vector, add it to the third vector, and you would work the law of sines and cosines repeatedly until you got it completed. But if you do it with Cartesian vectors, you simply decompose each force vector into ij, ij, ij components, and then the sum of the i's, because they're all along the same direction, is very simple, and the sum of the j's is very simple as well. So probably the best thing to do is that when you start this process, express each force vector as in Cartesian vector form as something I plus something j. We just did this one, isn't it? Right? What was it? Was it 66I plus 88j with Newton? How about F2? We want to put it in something I, something j. What would F2 be? Yeah, 50 plus 0, and that's Newton. And then F3, the hardest one. It's something in the I, something in the J, and let me pause, walk around. Let's get 5 people to get F3 correctly shown in this representation. All right, let's pick it up here. One thing I've encouraged you to do is sit next to a friend, make a friend, talk to your friend. There's no prohibition on that during this type of work it out. And every now and then I'll encourage you, like, okay, your friend's got it right, but you don't. Look at what your friend's got. But we take this and we bust and we look for a right triangle. That one is probably an easy right triangle because one of the angles is given to be 18 degrees. Oh, you could work with this as the right triangle, but then I've got to do 90 minus 18 to get this one, or I work with 18 down here because of that. But I think that's the easiest one. Did most people form this as their right triangle visually? Yeah, and then we have the hypotenuse of magnitude 70. And then I know that this edge right here, this edge right there, is how much goes back in the x direction. And this length right here, that side represents how much it's going down in the y. And so I right away take ownership of my signs. I know they're going to be negative, negative. And then I have this right triangle. Sometimes it's better to go ahead and blow it out so it's easier to see. This is 18 degrees. This is 70 newtons. And so this is, maybe I leave this like this. This is my hypotenuse. This is my opposite. This is my adjacent for that interior angle of 18 degrees. And then I remember, oh, if I'm looking for the magnitude of the opposite length or force magnitude, it's the hypotenuse times the sine of my 18 degrees. Or f of the magnitude f of x is equal to the 70 newtons times the sine of 18 degrees. The first time you do a few of these, you got to go slow. So this is probably a good time to tell you my little story. I was years ago, there were some kids playing piano, and I was listening to them, and the brother would sit down and play piano, then the sister would play piano, then the other brother would play piano, and the other sister. So I started talking to them. They were pretty old, 12, 14, 15 years old, and I asked them, how do you get good at playing piano? Practice. That wasn't too surprising, but then I noticed that the skill level wasn't the same between the brother and the sisters and all the kids in the family, in the same family, and roughly the same age. So I asked him, he said, you know what, it's very interesting, is my sister can play, but she has trouble with this part right here with these notes. It's like something in your brain and your fingers, but I get right through that section. I just blink, 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 and then, but my other one, has to go. And so what you do is you go real slow when you find a difficult part that you can't play well. And you kind of get it down, and then you go a little faster and until you can go at the right speed. And that's the same in engineering and statics and a lot of other things. Practice. And then if you find that you go slow right here, just think about maybe walking along an ice-covered sidewalk. Go slow because you slipped and fell before and it's very painful. Or go slow on the keyboard until you get it right, making sure you're confident every step why I'm doing it. And then before you know it, you'll just be going really fast through these problems. Okay, now this doesn't account for that negative sign, does it? Nope. We have to take ownership of the negative sign because of what right triangle we worked with. Yeah. And we see that, this is in that, what people were saying as I walked around, third quadrant. Yeah, this is going to be in the negative x, and this is going to be in the negative y. That's why I put the negative sign right away. And so what does this work out to be in the negative x? I forget. 66? No, is that right? No. There it is. 21.63. And then for the y, that will be 70 newtons times, not the opposite, but now the adjacent, the cosine of the 18 degrees. So that becomes, looking at my notes, 66.57. Both of them are negative. Sometimes somebody would get them switched. So every now and then I encourage you to pause, take a look, and it's larger in the down direction than it is in the backward direction. Yes, sir.
The easy way to avoid getting confused is to not use 18 degrees, use 252 degrees, which is
You can definitely do that.
the entire way.
Yeah, you could say, look, I'm going to always work from the x direction, and I'm going to always work counterclockwise. And then what I'm going to do is, even though the triangle's looking like this, with that being 18 degrees, I'm going to work with a right triangle conceptually that starts here, but then gets distorted. If that works for you, as long as you don't have errors.
I think you have the sine and a cosine switch. F of x will be.
Oh, yeah.
Cosine.
No, this is sine, opposite, adjacent, cosine.
So if you're going in the x direction, wouldn't you multiply?
We have this right triangle right here, and we identify the hypotenuse.
Oh, you're going relative to.
And then we pick whatever interior angle we want to work with. If we want to work with that one, this is the opposite for that 18 degrees. You could have said, look, I want to work with this interior angle. Okay, well, that interior angle is 90 minus 18. And then for that interior angle, this is the opposite.
Right, so then that would be the cosine.
Yeah.
Okay.
Yeah. Again, I say go slow here and go real slow until we master it. Some students were ahead of us. Some students need to really make sure not to have an error in any of this. Okay, then we think our three numbers to add for the I, and then we have our three numbers to add for the J, and what does it come out to be? I'm looking for my notes. Maybe I have it on the next page. Yeah, it comes out to be 94.3 in the X, 21. So this is our final answer. You take a look at it. This is a pretty strong force, and this is 50 newtons. Yeah, it's going to probably pull it more in the positive X direction. That's what we're showing. And then we look, this is pretty strong pulling up. This is down, but looks, and this doesn't really pull up or down. It looks like it's going to be up a little bit. And so there's our resultant force. Now, what is the magnitude of that resultant force? I'll pause, let you calculate it. This is a confidence builder in case I diminished your confidence on the previous problem. Right? Kind of like
Soft, hard, soft, hard.
So to answer part B, we used somebody's theorem. It was Pythagorean's theorem. So basically the square root of those squared, sum, you add, whatever. So we come in with 96.77, or should I be clear on that? It's f of x squared plus f of y squared. Bingo. Yeah, okay, so now I do ask, what is its direction measured counterclockwise from the positive x direction? So somewhere you can think of this force vector going out 95, up 21. It's going to look like this. What is that angle measured from the x-axis in the counterclockwise? Isn't that direction? Yeah. So we want this angle theta right there. And it comes in at 12.8 degrees. True? How would you get it? Arctangent of opposite over adjacent. There you go. Now we move into 3D. Oh, there's more problems we could solve with 2D. But we're going to move into 3D. And when we move into 3D, we need to think about our coordinate system. I know that the book talks, we're going to use a right-handed coordinate system. First question, is there any other coordinate system that you want to use? Is there a left-handed coordinate system? Not that I've ever seen in any book. So, but anyway, it's a right-handed coordinate system. Why do they call it a right-handed coordinate system? because you really need to have a consistent orientation between the I and the J and the K, between the x-axis, the y-axis, and the z-axis. Have to have a consistent orientation. It's not going to make a big difference until you get the cross products of vectors. But the cross product of vectors, the way it's formulated, is only for a right-handed coordinate system. You could have an incorrect left-handed coordinate system, think it's a right-handed coordinate system, put in vectors and sum them all day and all night, it would work. But if you ever started to do cross products, and we're going to need to do cross products when we do moments of forces, we must use a right-handed coordinate system. So this is hopefully an easy review. Most coordinate systems in this textbook have kind of a x, y, and a z. The z goes up. Okay, is that a right-handed coordinate system? As shown. Okay, it is. Yes, it is. How do you test it? Well, first of all, you pull out your right hand, and there's a number of ways to talk about it. You either pin the origin in the palm of your hand. I like to think of that. Pin the origin in the palm of your hand. Take your fingers and move them in the positive x direction in your mind, or try to orient it with the picture. Now that your palm of the middle of your hand is the origin, and you have the fingers pointed in the positive x direction, with the right hand, you can only curl your fingers 90 degrees one way. Curl your fingers 90 degrees one way, and that has to be the y direction. So conceptually here, I would get my origin there, put my fingers in the positive x, curl my fingers in the direction of positive y, and guess where my thumb is pointed? In the positive z. So hopefully you can do that. Now last time, I don't know why, I had a student, it's like, oh, I can't understand this. See me in office hours if you need a little extra help with this. But let's work through a few problems. Let's just pick a few of them. Each one, solve it on your own, with your own right hand. Don't try and do this with the left hand. It won't work. You must use your right hand. There's a coordinate system. Is it a right-handed coordinate system? How do I tell? Put the middle of your hand at the origin, point in the positive x, take your fingers, curl to the positive y. Which way is your thumb pointed? Is it pointed in the positive z or not? Yes or no?
Yes.
Okay, you gonna see that? This book is very, very good. There are no incorrect three-dimensional coordinate systems in this book. Are there some non-right-handed incorrect 3D coordinate systems in other books? Yeah. Just look, you'll find them. But basically, this is a no good. No. Right? To fix it, the z should have been up that way. Okay? But again, unless you're doing cross products, then it really doesn't matter. So some books, they can do whatever coordinate system they want. It's not going to matter. Let's look at this one. Is this one a right-handed coordinate system? Use your right hand and test it. What do you think? You're getting better at it, huh? Where do we put the origin? Keep our fingers straight out. Point them in the positive x direction. Curl 90 degrees. Sometimes you have to rotate your hand to make it work. Curl to the positive y. And what do you think? What do you think? Good or no? No, good. Right? All right? We got more of these. Do you want more or what? Or call it quits. All right. We want to be able to represent a force. That's a vector in 3D. Well, here's a force represented in 3D. Well, when you start, I would construct what they call, don't you love these words? A rectangular parallelepiped. Yeah, it's a rectangular parallelepiped. Such that all of these interior angles are 90 degrees on this parallelepiped. And a parallelepiped has the two sides and the two sides and the two sides parallel. But if it's rectangular, it's basically not a cube, but a rectangle. what they call a rectangular parallel pipette. I mean, if it was a cube, then this length and that length and that length would all be the same, but they're not necessarily all the same. And now what happens is this helps us visualize where that force, it starts at the origin, where it ends. It ends at this opposite corner of my rectangular parallel pipette. And that really helps us decompose or express it. We can see that this force is going to have a sum of so much travel in the x, so much force in x, so much in the y, and so much in the z. So it's like if I add these three forces, the resultant will be that single force that cuts across the diagonal of my rectangular parallel pipette. So this here is f of x, f of y, f of z, the magnitude of the travel in the x direction, of the y direction, of the z direction. So the general representation of the force is f of xi plus f of yj plus f of zk. 2D was easy, 3D, we have to work on the visualization a little bit. So what they often do when they have this pipette is they throw a projection down into the xy plane and they'll draw that line. It's a projection of the force into one of the planes, often it's into the xy plane. And from this projection, they will construct a right triangle to help you visualize it, and another right triangle to help you visualize it. Here is that blue. It's often they're color-coded blue or some sort of tan. Oh, Professor, you told us we're going to get really good at right triangles. Yeah, you are. Here it is. Do you see the two right triangles that help describe the orientation of this force vector in 3D? Sure. So with that, we can now decompose. But a lot of times the students will look at these colors and they'll get very confused. They'll get very confused, like, I don't understand what this blue shaded triangular look is telling me. I don't understand what this tan shaded triangle shape is telling me. Try to get the projection of that force into the xy plane. I think that helps. Identify two right triangles. One of them will be shaded blue, one of them will be shaded tan. And now use your opposite and adjacents to work through the problem to decompose it. Okay, here it is. Oh no, they took away my parallel pipette. But basically, they only give me my two triangles, don't they? All right, so express this force. It's a 320-pound force. As shown in this coordinate system, express it in Cartesian vector form. So what is it going to be in the I? What is it going to be in the J? And what is it going to be in the K? And you've got to work slowly or you make an error typically. You've got to be correct. Okay, we've got 2 minutes, which means we don't have time to solve this problem, which means I'm going to pick up here next time. All right? But you should be able to solve this problem. Please work on it. I won't see you till next week, Wednesday. Monday's a holiday. Okay? Work on mastering engineering. Come to my office hours if you have any questions about right-hand rule, right-handed coordinate system, a lot of things. I'll be in my office right after this class. Thank you very much for your attention.